Thank you, Professor Patterson. Good morning, ladies and gentlemen. My name is Akasaki. Aka means that in Japanese, but today I'd like to talk to you about blue light. May I take a seat? Following introductions, I'd like to talk about the creation of a gallium nitride single crystal with excellent quality, then development of gallium nitride PN junction, blue light emitting diode, and laser diode. Finally, I'd like to summarize my talk. In the 1960s, red and green LEDs were already realized, but there was no prospect of blue light emitting diodes even in 1970s. The energy of a photon emitted from LEDs is approximately equal to the energy gap of semiconductors that is being used. The wavelength of blue light is ranging from 458 nanometer to 480 nanometer, equivalent to 2.6 to 2.8 electron volts. So, two requirements for creating blue light emitting diode are A, the so-called wide gap semiconductors with energy gap of about 2.6 electron volt or larger should be used. B, it is definitely advantageous to use direct transition type semiconductors which have high emission efficiency because electron momentum is being conserved while emitting light. Moreover, A and B are not sufficient conditions to realize high-performance LEDs. It is essential to grow high-quality single crystal and to produce PN junction to conductors which satisfies the above requirement. Some semiconductors have hole that is electron deficiency than electron, which called p-type. Others have more electrons than hole, they are n-type. Our structures with the junction of p and n-types is a PN junction, which enables highly efficient light-emitting diodes and solar cell and transistor and so on. In the PN junctions, bias with forward voltage, electrons are injected from the N to the P side, and holes are injected in the opposite directions. Electron recombines with hole, and light is spontaneously emitted. In 60s and 70s, candidate materials of blue light emitting diodes were zinc selenide and gallium nitride. For both materials, however, growth of single crystal and realization of PN junction were impossible at that time. When it is difficult to grow single crystal, one must rely on heteroepitaxial growth on this similar substrate. Zinc selenide film can be grown on gallium arsenide, of which lattice constant close to those of zinc selenide. Thus, many researchers have been working on zinc selenide. I myself, however, worried about the instability of zinc selenide. On the other hand, gallium nitride is far more stable, both physically and chemically. mistype. That is not p-n junction, but metal insulator semiconductor structures. But this report accelerated the R&D of nitride-based blue LEDs. In the mid-1970s, however, almost researchers withdrew the development of gallium nitride devices because they could neither grow high-quality gallium nitride single crystal nor p-n junction, both of which are indispensable to develop high-performance blue LED. Besides, at that time, theoretical studies indicated the instability with achieving p-type gallium nitride and zinc selenide due to self-compensation mechanism. Despite such stalemate, while I was working at Matsushita Research Institute, Tokyo, MRIT for short, I chose gallium nitride in 1973 because its toughness and wider direct energy gaps and non-toxicity, aiming at the development of high-performance p-n junction type blue LEDs. I started to grow gallium nitride by molecular beam epitaxy, MB for short, in 1973. Then, by hydrogen vapor phase epitaxy, HVPE for short, in 1975. And in 1978, my group at MRIT developed a mistype blue LEDs, which was far brighter than anything one had before. Although it was no comparison to p-n junction LED, which we invented later in 1989. During this work, I recognized the great potential of gallium nitride as a glue luminescent material. When I found tiny but high-quality crystallite embedded in a gallium nitride crystal containing many crack and pit, I was intuitively convinced that conductive control, even p-type crystal, should be able to be achieved if this kind of quality over an entire wafer could be made. Thus, I made up my mind to go back to the beginning, that is the crystal growth, in 1978 at MRIT. This decision, I think, as a major turning point in not only my own gallium nitride research, but gallium nitride R&D throughout the world as well, which had been stagnating at that time. Let's move on the creation of gallium nitride single crystal with excellent quality. Crystal quality is greatly affected by the growth method and condition. Epitaxial gallium nitride can be grown by HVPE, MBE, or metal-organic VPE. This is MOVP for short, also called MOCVD. In case of HVPE, crystal quality was degraded by appreciable reverse reaction and the growth rate too fast to fabricate device structure with thin layers of nanometers. MBE was prone to nitrogen deficiency, and the growth rate was slow at that time. On the other hand, MOVP was developed in 1971 by Manasevich et al., but had been never employed for the growth of gallium nitride thereafter, seemed to be more suitable for the growth of gallium nitride because this method has no reverse reaction, and growth rate and the alloy, I mean that alloy is aluminum gallium nitride and gallium indium nitride alloy composition, and also impurity doping could be readily controlled by the varying the flow rate of the source gases. Thus, I decided to adopt MOVP as the optimal growth method for gallium nitride and related alloy in 1979 at MRIT. Today, gallium nitride and related alloy are mostly being grown on sapphire by MOVP by this method. In 1981, I restarted working gallium nitride growth using MOVP in collaboration with persistent graduate student Yasuo Koide and Hiroshi Amano, who put a lot of effort into crystal growth at Nagoya University. Even with MOVP, however, it was not so easy to grow uniform films. After much trial and errors, we made an innovation and improvement in the growth method and condition. First, Koide increased drastically the flow rate of the mixture of organometallic gases and hydrogen gas to about 110 centimeters per second from the previously only 2 centimeters per second. And he also blew the gas onto the substrate inclined at about 45-degree angle rather than placed horizontally as in the previous attempt. We were thus able to suppress convective gas streams on the heated substrate and make the gas flow smooth to achieve the uniform films. Even though the film thickness was now even for the entire beaker, there was no substantial improvement in electrical and optical property either, which suggested the presence of a lattice defect and impurities. This would be, for the most part, be due to the huge lattice mismatch of 16% between gallium nitride and sapphire as substrate, I suspected. In fact, for the epitaxial growth of semiconductor, it is considered to be gospel to have lattice matching as growth of silicon on silicon. And in the case of a heteroepitaxial growth, even a mismatch of 1% would make it difficult to grow high-quality single crystal. To overcome this issue, we developed the low-temperature buffer layer technology in 1985. This is a method to deposit materials with physical properties similar to those of gallium nitride and sapphire to make a buffer layers of a thickness of about 50 nanometer, which is thin enough not to interfere with the transmission of crystallographic information of substrate to the epitaxial layers at a temperature, say, several hundred degrees centigrade. That is considerably lower than the temperature for growing single crystal of gallium nitride. The growth temperature would then be raised to the epitaxial temperature of about 1,000 degrees centigrade to grow gallium nitride single crystal. For the buffer layer material, I considered aluminum nitride, gallium nitride, zinc cell oxide, or silicon carbide. In addition to the first improvement, Hiroshi Amano carried out low-temperature aluminum buffer layer technology combined with a further accelerated gas flow rate of about 430 centimeters per second, and succeeded in the growth of gallium nitride single crystal with a specular surface in 1985. Details will be presented by Professor Amano. Gallium nitride grown with low temperature buffer layers obtained by Hiroshi Amano has specular surface with no pit and crack, and also is quite transparent. Not only the crystal quality in the green letters and electrical properties, black letters, and also the luminescence properties, green one, of gallium nitride have greatly been improved at the same time. It was the tenacities of Hiroshi Amano that we finally identified the optimal condition after his overcoming countless failed attempts. The thrill I felt when I saw the gallium nitride crystal with an ideal form and content is simply unforgettable. It was something that I had dreamed of realizing ever since 1973. Today, the low temperature buffer layer technology in MOVP is indispensable and standard in the growth of high-quality gallium nitride and its alloys. This shows the scanning electron micrograph of surface taken by Kazumasa Hiramatsu. Number one is as deposited low-temperature buffer layers consisting of many nanocrystallites embedded in aluminum nitride amorphous layer, and 2 to 5 are gallium nitride grown at about 1000 degrees centigrade on the buffer layers for 5 to 60 minutes, respectively. With raising the growth temperatures, the lateral growth of gallium nitride dominated, resulting in a flat surface at 60 minutes growth. On the other hand, right-hand side, in the case of direct growth, gallium nitride with hexagonal column with different height and size grew, remaining bare sapphire surface even for 60 minutes growth. The essential role of the low temperature buffer layer was found to be the supply of the nucleation centers having the same orientation as the substrate and the promotion of a lateral growth of the epitaxial layers. Let's turn now to the realization of P-type conduction in gallium nitride. To realize P-type conduction, we repeated zinc doping of high-quality gallium nitride, but no P-type gallium nitride was produced, although the crystal became highly resistive. In 1888, Hiroshi Amano found that low-energy electron beam irradiation enhanced markedly zinc-related luminescence intensity, remarkably enhanced, while the spectral shape remained unchanged. we suspected that the Fermi level of sample had been changed potentially to the p-type. Yet the sample did not exhibit p-type conduction. According to J.C. Phillips, the difference in electronegativity between magnesium and gallium is smaller than that of zinc and gallium, suggesting magnesium might be shallower acceptor than zinc. That means more easily ionized. In the early 89, Masahiro Kito carried out the magnesium doping of high-quality gallium nitride crystal using bicycle pentagenyl magnesiums, then applies the low-energy beam electron irradiation to the sample and found that the magnesium-related blue luminescent intensity had been markedly enhanced, while the spectrum shape remained unchanged, and that the sample had been converted to resistive p-type crystal. Immediately, we fabricated the PN junction LED by hand. An electric current is only being passed through the centered LEDs, which emitting light. Also, we demonstrated more encouraging IV characteristics than we had ever seen LED. The site of a piercing blue light emission from the first ever gallium nitride PN junction blue LEDs amazed me all over again. We went on to the development of the world's first p-type aluminum gallium nitride and p-type gallium indium nitride in the same manner as the case of gallium nitride. Now, I'd like to show you conductivity control N-type nitride. In the meantime, we noticed that the use of low temperature buffer layer resulting in marked decreasing in the residual donor concentration, causing the N-type crystal to have a high resistivity. In the real setting of device fabrication, conductivity control over a wide range is needed. In 1989 to 91, we achieved a conductivity control N-type gallium nitride, also N-type aluminum gallium nitride, ranging over about 2 orders of magnitude by silicon doping using silane, while maintaining the high crystal quality by means of a low temperature buffer layer technology. Conductivity control of these N-type alloy allows the use of heterostructures and quantum well in the design of more efficient PN junction light emitting structures. This method of conductivity control of N-type nitride is also in widespread use around the world. In the 1990s, we achieved the stimulated emission in the UV region, ultraviolet region at room temperature for the first time with 1 order of magnitude lower optical power than before from the high quality gallium nitride. And in 95, first stimulated emission by electric current injection using high quality quantum well devices. And also, we developed in 96 nitride-based laser diodes and also the ultraviolet laser diode. This graph shows that the number of papers and activity related to nitride materials and devices over the years. All events are marked in the years when they are first achieved. It is clear that development of gallium nitride devices started in early 70s, but declined until mid-1980s. The start of a steep increase in number of papers and accomplishment is due to the key invention, that is a high-quality gallium nitride single crystal by low-temperature buffer layer technology in MOVP growth, and gallium nitride PN junction blue LEDs in the late 1980s. In summary, while many researchers abandoned the development of gallium nitride blue light emitting diode, I have been fascinated the research of gallium nitride-based semiconductors since 1973. Through persistent effort with the collaboration of Hiroshi Amano, Yasuo Koide, and many students and co-researchers over many years, we invented high-quality gallium nitride single crystal in 1986, and gallium nitride PN junction blue LEDs in 1989. Gallium nitride-based photonic and electronic devices are environmentally sound, robust, and energy-saving, which benefit humanity. I'd like to express my sincere appreciation to many collaborators at Matsushita Research Institute, Tokyo, numerous students at co-researchers at Nagoya universities and major universities, and Professor Bo Monema for their great contribution throughout this research. My special thanks go to the Toyota Gosei Company and the Toyota Central Research Laboratory for their cooperation in the development and production of gallium nitride-based materials and devices. This research has been financially supported by the MITI at that time, and the MEXT and Japan Science Technology Agency, and JSPS. Thank you very much for your kind attention.